And we're recording. Okay, so real quick review of what we did recently in developing this idea of surface integrals. So first of all, if you want to chop it up, add it up, or argue that the whole is the sum of the parts, yeah, you can do that on a wide variety of different kinds of domains. We talked about intervals. We talked about two-dimensional regions in the plane, three-dimensional regions in space, then eventually curves in space, and now surfaces in space. And structurally, it's always the same idea. It's break it up into little pieces, and then on each piece, quantity per unit size times size. Adapted appropriately to the circumstance. Here, size is two-dimensional, so it's area, and so, but other than that, it's the same as all other Riemann sums that we've ever written down. Notation, terminology. We talked about how to compute by doing basically a pullback argument, right? Parameterizations give the opportunity for a pullback. Examples, right? Multiple examples. And then we tried to apply these ideas to a different kind of a quantity, namely flux, and we ended up with some issues. First of all, what we found is that, look, in order to even make sense out of flux, we have to decide what do we mean by the positive direction through a piece of surface. Whichever of the two unit normal vectors you pick, that dot product's going to give you opposite values in either of these cases. So we have to decide, wait a minute, which one are we talking about? Right? So in other words, you have to talk about not a surface, but an oriented surface in order to make sense out of how to apply these tools we've been developing to flux specifically. This is intrinsic to the application. It's the real world notion of flux that forces us to do this, right? Mathematicians didn't just decide they wanted to, right? This is from the physical reality. So we developed this idea of a vector surface integral, which again has a vector differential and a vector integrand, right? Again, that all effectively comes out of the nature of the physical application, right? Okay. Then we, develop a computational formula for how to actually crank this out, and we did an example. We entertained a portion of a parabola sitting over the unit square, and we computed the flux using that formula. And then we entertained the question of, wait a minute, where in here did I even consider this idea of orientation that we just got through agreeing has got to be important. The orientation's got to be in here somewhere. How did orientation appear in this calculation, and why didn't I make a thing out of it? Okay, so, well, right here was where the problem was, right? Again, confessed in advance. The issue here, fleshed out now here on the next page, is that, you have to think about how you parameterize. And when you parameterize, you might end up parameterizing right side up, or you might end up parameterizing upside down. Just two possible orientations that could have come attached to the surface. The nature, what we call the orientation unit normal, this is intrinsic to the question. The parameterization is something that you make up on your own, right? And so when you talk about the parameterized unit normal, it's a coin flip as to whether that will be the right direction or the wrong direction, right? And this is about where we left it last time. So I'm going to continue on from this point now, but the issue that we're going to address is how do I know if I might have parameterized upside down? How can I avoid accidentally parameterizing upside down, and how do I deal with it if I find that, I did parameterize upside down? Okay. All right, so here we go. So we're going to reconsider almost exactly the same question the same example that we looked at previously. Same vector field, same surface, and so because it's the same surface, we're going to use the same parameterization. Graph parameterization, right? It's an easy choice to make. You gotta love it. It's very convenient to do. So the partials are the same, the cross product is the same, and you could kind of take this and plug and chug and run with it, except Now is the time. This here, once you've computed your parameterized unit normal, this is where you have to pause and take stock and ask yourself, wait a minute, did I parameterize this right side up, or did I oops it and parameterize it upside down? Okay, so how do you tell? You tell by looking back in the statement of the question. And you see here, I deliberately glossed over it as I talked through this example a second ago. But it says right here in the statement of the question, we're interested in the flux downward. This is telling me that I want to use, that my orientation unit normal vector that comes with this oriented surface, what the question is about, in other words, it's a downward normal. Have I gotten a downward normal? No, my z component's positive. This is, upward-ish, you might say. So I parameterized backwards. I parameterized up when I should have parameterized down. I got it wrong. Does everybody see the problem here? These are different. These are negatives of each other, and so I'm off. Let me pause there. I want to make sure everyone sees what the problem is before I go on and address the next thing. Okay, how do I deal with this? Right? How am I going to account for the fact that my parameterization is the wrong way? Oh gosh, I'm not going to reparameterize. I don't need to reparameterize. Beautifully, what I know is that I've parameterized not just the wrong way, I've parameterized exactly. This is a good thing. Exactly wrong. Exactly the negative of the parameterization that I should have done. So that means that my answer is going to be off by a minus sign. I'll fix it by inserting an extra minus sign. It's as easy as that. Okay? So we see that no, we got this wrong. Our parameterization is backwards. It's up when it should be down. And we resolve it by sticking in a minus sign right there. And we're good to go and go about your business. You don't need to reparameterize anything. Just perfectly fine to use the wrong parameterization. Just fix it. Everybody see? Okay. All right. So very often students ask, well, how can I avoid doing this in the first place? How can I look at a parameterization and tell? And the sad truth is that I think it's just more trouble than it's worth. I mean, I could make up certain rules that work in some special cases, but I have to be extremely careful about how I state such rules, such as, graph parameterizations, always blah, 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 or what. Now you gotta worry about, which order do you, what's the ordering of the parameters, and did you associate them to the XYZ in the same, or, compatible or incompatible order? It's sticky. It's not worth it. My advice is don't worry about parameterizing right side up or right side or upside down. Just parameterize. Go ahead and compute. And when you get to having identified your capital N vector, at that point, then address the question. Realize that you may have been wrong, and then deal with it accordingly. It's just not worth trying to get it right in the first place. Does that make sense to everybody? Okay. Now, there's one last little sticky issue that I do want to talk about. I think this is important. So, where you insert the minus sign matters. It really matters. Specifically, let's think about this ds vector here. This ds vector is pointing in a certain direction. What governs which direction this is pointing? What governs it is the statement of the question, the oriented surface you were given. That's what decides what direction that points. What decides what direction this thing here points that I seem to have replaced it with? What controls the direction of capital N? It's the parameterization. It's not got anything to do with the statement of the question, right? This capital N comes directly out of the parameterization. It is defined by formulas that are explicitly in terms of the parameterization, right? So you have to insert your minus sign there. You cannot just say that, oh, these are equal, and then blah, 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 and then later at the very end insert a minus sign. It has you writing down statements that aren't true, right? So let me point out, for example, where would be the falsehood? Let's imagine that I were, not concerned about the reasoning, focused only on the final answer, and I argue that, well, who really cares if I just, remove that, and let's suppose that I just put my minus sign here only, right? And let's think of what I've got written down. What I have written down on the page as a result of making this wrong choice is the suggestion that these two things are equal. They aren't. They are negatives of each other. Not true. Right? You can't have false reasoning on your page. That's not what we do, right? Keep in mind, this course is about reasoning. It's not about whether the answer at the end is in the box is numerically accurate. That's just not what the course is about. So this statement that I have implicit in what I've, written down here, ds equals capital N dsdt, that's false. They're not equal. And then there's another sign error in the statement that, again, keep in mind, we've put our minus sign right there. We have another false statement in the suggestion that this integral is equal to this. No, it's not. These are negatives of each other likewise, right? Because this one got a minus sign, and this one didn't get a minus sign. So again, these are negatives of each other. You can't say they're equal if they're not equal. So your placement of where you put the minus sign, you realize you've got a minus sign to stick in there. Where you put it matters to the tune of two significant falsehoods on your paper. So you got to make that choice appropriately, and where those minus signs are in your reasoning really matters to whether your reasoning is valid or whether it's not valid. Does that make sense to everybody? I know it seems like it's a finicky, uptight kind of a point, but it's very important that your reasoning be valid reasoning. Okay. All right. So, in fact, where you should do this is wherever you make this transition, wherever you go from stuff defined in terms of the question's orientation to stuff defined in terms of the parameterization's orientation. When you make that transition, that's where you have to first insert your minus sign, because those are the things that if you parameterize wrong, those are the things that are actually different. Okay, I hope that's cool for everybody. And with that in mind, we'll basically move on. I guess I'll make the observation that this flux that we're trying to compute, it's all over but the shouting here. This can all be multiplied out. It's a polynomial. The bounds here are constant bound. This is an easy double integral, effectively. So blah blah blah. Okay, now I do need to say a couple of things about language. It says here oriented downward. Does that mean that the normal vector, that my orientation unit normal is exactly straight down? No, it doesn't. And you can tell it couldn't possibly be, because this is perpendicular to my surface. It's not exactly straight up or down. It's got other stuff going on here. So that's not what we mean when we say downward. The language that we use when we're talking about orientations is necessarily a little sloppy. Let me talk through an example. Here's morally the example we were just looking at. Here's one orientation, a collection of unit normal vectors. And then here's another candidate orientation, collection of unit normal vectors pointing the opposite direction. Why would I say upward versus downward to distinguish these? The greens are not uniquely upward. The blues are not uniquely downward, right? But what I can say is that the word upward unambiguously distinguishes the green one from the blue one. All the green vectors are at least somewhat upward. None of the blue vectors are in any sense upward. So this word upward could only possibly refer to one of these two candidate orientations. So it's entirely unambiguous, even though it's not precise, right? It's not telling me the exact formula. In some sense, the whole point to using words is that I don't want to have to describe it with only formulas. I want to describe it with convenient language. So we accept the fact that that's a little bit sloppy. Likewise, when I say downward to refer to this blue orientation down there, well, not exactly downward, but this is the only of the two orientations that's in any sense downward. All the green vectors are in no sense downward, not even a little bit. They're somewhat upward. So, just, be aware of this kind of, language issue. And now there are other choices that you can make. Again, there's a little bit of sloppiness is kind of understood. These green vectors here, the ones that I previously called upward, I suppose you could kind of call them inward. I put a kind of a on this because there is no inside on this surface. Right? This surface does not contain a region. There is no inside. And so inward, nobody would misinterpret what you meant with complete confidence, right? If you said inward. And yet it is unnecessarily awkward when upward does the job just as well, if not better. In fact, definitely better. So use the better term, all else being equal. Okay, how are we doing? Everybody with me? Yeah.
The surface is like a bowl, right?
Yep. Okay. Yep, that's right. Yeah. Alrighty. Okay, so now keep in mind there are different geometry situations that you have to be prepared to describe geometrically. Let's look at this sphere here. Here are my two candidate orientations. There's this green one that I've got, and then there's this blue one. How would I distinguish the green from the blue in the case of this sphere? Upward versus downward does not cut it. It not only is it sort of it's unacceptable, right? Because which one of these is distinguished by being upward? Some of the green vectors are upward, but some aren't. Some of the blue vectors are upward. Some aren't. The word upward here, just absolutely unacceptable in distinguishing the blue from the green orientations. It just does not do the job. Does everybody see how that's not okay? Right, but no problem with the word inward here. All of the blue vectors are inward. None of the green vectors are inward. So inward does unambiguously distinguish these two options. Okay, so various different versions of this. Think about the geometry. One more example, down here. Feel free to take a look at this. But just make sure that when you're choosing language to describe your orientation, make sure to think very carefully about what words you're choosing, and does your verbiage unambiguously distinguish what you need it to? And then likewise, when you interpret, like if you see in a statement of a question, if they say upward, and if from this, if you assume that means that your unit normal vector is 0, 0, 1, well, that's just wrong. That's absolutely misinterpreting what was intended by that choice of words. And it's not a sympathetically kind of wrong either. It's just really, really fundamentally wrong. So heads up about that. Don't misinterpret the language there. Okay, is everybody okay with all of that? All right, moving along. More good news. Lucky coincidences happen, right? Again, I cashed in on these kinds of things many times in the undergraduate career that I had and that y'all are about to embark on, right? So, a little differences between engineering and physics, but nevertheless, really important to be on the lookout for this sort of thing. So, let's suppose, for example, that you want to compute a flux, and you got a vector field given, and you've got a surface given. And how do you compute this flux? And the brute force approach on this would be to parameterize your surface. Well, your surface you would probably parameterize with the spherical graph parameterization. I certainly would. That means you're going to have trig all over your integrand. You're going to have trig all up inside of your surface differential. And you're going to have just trig everywhere. Lots and lots and lots of trig. Half-angle formulas and angle addition formulas. And it's a nightmare of inconvenience. Doable, but inconvenient. So what I recommend instead, just in case, always be on the lookout for possible freebies, possible opportunities to turn an otherwise hard problem into an easy one. Right? And notice what I've done here. I haven't even parameterized this surface at all. I don't need to parameterize it because I observe from geometry, right? Gotta love this word right here. Spheres. Spheres are awesome. They have fantastic symmetries. One of which is that the normal vector to the surface is always a scalar multiple of the position vector at that point on the surface. This is a sphere centered at the origin, of course, I meant to say. So that's really nice. Knowing that it is a scalar multiple of my position vector allows me to write down a really easy formula for my normal vector. And so just stick it in there and see what happens. You might get lucky. This is well worth the very small amount of effort that it takes to try that. Now, I mean, other than trying it, I can't give you much of a motivation for how can I see in advance that this is going to work. Try when the opportunity presents itself, right? But in this case, notice it works great because using this formula for my normal vector and taking the given description of the vector field, you can just instantly notice that this dot product and therefore the entire integral 0. We walk away. We're done. We didn't have to deal with any trig at all. Everybody see what happened there? This is a pretty neat trick when this kind of thing comes up. And again, you'd be surprised. The world is full of symmetries. The world is full of good news. And this happens to a worthwhile extent to be aware of it. Okay. Questions on this one? Does everybody follow the geometry? Okay. All right. Okay, here's another example. Now, this is a different kind of geometric good fortune. So, it's not always going to be one form of good luck there's different kinds of things that you can kind of piece together little pieces of good luck, and all together things can work out great. So just again, always head on a swivel, always be looking for where's my easy out so that I don't have to parameterize. So here we go. We're going to look at a surface that's it's a part of this plane y equals 3. Specifically, it's the part described by a certain inequality. So there's my actual surface, and oriented in the positive y direction. We'll come back to that in a second. And I've got a vector field given, and I want to compute the flux. So how am I going to proceed here? Well, let's start by thinking about the normal vector in question. Here's my surface. Notice my surface is certain complicated things about my surface. I've got a quartic issue here. For one thing, that's annoying. But more importantly, it's sitting inside of this plane. And based only on the fact that it's sitting inside of that nice flat plane, I can immediately infer that my normal vector, given that it's in the positive y direction, I can immediately infer if 0, 1, 0 is my orientation unit normal. Just very convenient. Everybody see that? Won't always be this convenient, but be on the lookout. Again, you gotta love planes, right? So, spheres are awesome and planes are awesome. So, again, you see something potential for awesomeness, think about the geometry. Figure out what you can conclude without getting into the algorithm, the parameterizing pullback plug and chug algorithm. Okay, so now what does that buy me? Knowing that the normal vector is 0, 1, 0. Yeah, it's part of the part of the point here. Here's the other part of the point. Knowing that my entire surface is inside of this plane where y equals 3 means that I get to plug in y equals 3 everywhere in my vector field, and specifically plugging it into the second coordinate tells me that second coordinate is 0. So that's another benefit that I get, basically for free, as a result of the fact that my domain is inside of a plane, a known plane. So looking down at what we've got then in our integral, there's still, stuff to be worried about, and there's algebra that hasn't just canceled immediately, but I know I've got a 0 there and a 0 there because of the normal vector, and I've got a 0 here because of the value of y, and how about that? My dot product, and therefore my entire integral, 0. Again, walk away, right? I didn't have to get my hands dirty at all on this question. Everybody follow all those steps? Questions, feel free. Look like you're thinking about a question.
Yeah, so the y equals to 3 can be plugged in everywhere. Right?
Yep. Oh, yeah. No, that's true. So you can plug in the y equals 3 there also. It's just that it doesn't lead to a payoff, so I didn't bother. Yeah, and I guess, that's the only other one. Yeah, just, so I was just trying to keep it streamlined. Yeah. Everybody happy? All right. Okay. So, y'all may recall when we defined vector line integrals, we ended up also defining something called coordinate line integrals. Well, now that we've defined vector surface integrals, here we are, we're going to define something called coordinate surface integrals. It's a little bit more it's a little bit harder to see coming, and there's some geometry involved in here that I've already kind of expressed sadness over this. We don't have time to cover some of the geometry that makes this really as intuitive as we could if we had an entire year in this course instead of only one semester. But anyway, here's what it is. All of this is old news. We've written all this down before, effectively, right? And you may recall specifically and pointed out that this formula for the capital N vector, there's some really cool geometry behind it, and this is what we don't have time to talk about. And that makes me sad. But we can just kind of proceed on this, and I can multiply out the scalar into the coordinates, right? Just distribute that dSdt scalar. And now let's look at this, and let's ask the question, what do you think we ought to call that thing? And I mean, we've seen exactly this expression in the past, right? When we were doing change of variables, two-dimensional change of variables. It's as if, it doesn't, but it's as if that cancels with that. And again, math crime, and apologies to the formality of it all. But we kind of know that this kind of really should be called dy dz. Now, the geometry that I don't have time to show you, that it would just take 15 minutes that we can't afford, gives a fantastic geometric justification why this is not just notationally convenient. This is geometrically natural. This is real. 15-minute discussion I don't have time for ensues. So I'm going to hope that you're all willing to buy that. And anyone who wants to see that argument is extremely welcome to come to office hours, and I'll be very happy to talk through it, or even if, a little time outside office hours. This is a really good one. I'll be very happy to show you, but we can't do it in class. So likewise, this is that, and this is that. And what we've got then is an alternative notation for our vector surface differential, ds vector. Okay, so what? Well, if you write that down, and then if you recall that our vector field also has coordinates, Again, typically PQR, not that it matters, but it's a very common choice, so I'm going to stick with a standard. Then notice, you get a dot product that you can just literally crank. And this dot product, of course, crank it out. Suggest you should write this down. And what we have then is this is called a coordinate surface integral. It is just an alternative notation for a vector surface integral. And you can keep track of, what is that thing? By analogously just keeping track of, let's see, dy dz. I see that dy dz is my first coordinate of my ds vector. And so that means that p, being what's multiplied by that, must be my first coordinate of my field vector. And likewise for the q and the r. So just an alternative notation. Now, what are the pros and cons of this notation? It is clunkier. That's the downside. It's also less geometrically satisfying in the sense that by itself, it's hard to make sense out of what R is. On its own, by itself, it relates to a natural thing, namely the vector field F, but it's not by itself really physically, fundamentally natural thing. And then likewise, what in the world does dx dy mean? I'm not in the xy plane. I'm on a surface. If my surface is kind of angled like this, what sense should I make out of dx dy? There's good answers to these questions. It's just a little, again, beyond what we have time for. But still, less geometrically natural. So this notation, kind of like coordinate line integrals, is clunky and awkward and opaque. So why are we talking about it, right? It's a seemingly very undesirable notation. And in the context of Math 219, I don't particularly encourage you to lean in this direction. Rarely does it have advantages in this course. But I do want you to know that, I hope you're noticing the analogies to the conversation we had in the past about coordinate line integrals. I claim that this relates to differential forms. And if you were to write down the differential form notation to represent this vector surface integral, it would look a lot like this. Not quite exactly. There's a little missing aspect of it that, again, we don't have time for. But this is highly suggestive of differential forms. Differential forms are bonkers powerful. Extremely good stuff. You can prove stuff with differential forms you just can't prove without them. Culturally, if nothing else, it's good to know that this is a real thing. But more to the point, because it is so natural and powerful, that's why this notation is also in common use. So you're going to see people using this notation, and a little bit in our textbook, and significantly, though, in your future courses, your future engineering courses or physics courses, whatever, this notation's out there. And so you need to know what to do with it when you see it. So my advice, when you see this notation, right, when you see all of this, is you should think, okay, all right, fine. Okay, so all of this here, this is just fancy notation for the ds vector. That's all it is. And so, therefore, these components, P, Q, and R, those are the coordinates of the vector field whose flux I'm computing here. Right? So just reverse engineer this little algebra and think in terms of, don't think in terms of that notation, think in terms of that notation. It's just, it's more natural, it's more compact, it's more relatable, convenient. For our purposes, it's more desirable. Does that make sense to everybody? Questions? Feel free, again. I emphasize, and I would encourage you, in fact, to look at this page about coordinate surface integrals, and then look back in chapter 6, wherever that is, where I talk about coordinate line integrals, and notice the analogies, very strong analogies between these two situations. Okay. All right. Symmetry theorems. I'm a fan. Good news, we have symmetry theorem for scalar surface integrals. It's morally equivalent to symmetry theorems we've seen in the past. I'm deliberately writing it on the page, both the theorem and the subsequent comments, laid out on the page deliberately as similarly as I can. I think I even did a copy paste and then made minor adjustments just for that purpose. So good news, symmetry works for scalar surface integrals. You need your integrand to be odd. You need your domain to be symmetric. You do need, I emphasize, for both of these conditions to apply, and you do need, can't emphasize enough, to use the same plane for both of those requirements. And with that said, yeah, cool, symmetry totally works. Awesome. Big time saver. Lovely result. I hope that's believable. Does anybody have any questions about this? Feel free to use symmetry arguments on scalar surface integrals. Okay, so fantastic. Now, the warning. This is specifically and only for scalar surface integrals. It does not work for vector surface integrals. If you try to make an odd symmetry argument for vector surface integral, it's nonsense. There is no such property or theorem. So now, why is there no such result? Well, I mean, here's a kind of a rough picture here. Keep in mind a vector surface integral looks like that. Keep in mind further, I can expand the ds vector, break it out into its sort of components. I've got my orientation vector, I've got my ds scalar, and you can talk about and make a persuasive case that, hey, well, yeah, but on opposite sides, this little piece of area and that little piece of area are the same. If you slice it up appropriately, then yeah, sure, that's true. But what is just not going to work is any claim to symmetries that you might make about the orientation vector. You look at this orientation vector here, you look at that orientation vector there, they are not the same. They're really, really not the same. They're also not negatives of each other. There's nothing, neither possible use, they're just different. Right? So it does not work for vector surface integrals. So heads up, please make sure not to step on that landmine. If you find yourself looking at a vector surface integral and you try to make a odd symmetry argument about your vector surface integral, it's all nonsense. So don't step on that landmine. Any questions about that? Is everybody fully appropriately warned and etc., comfortable with what the problem is? Full disclosure, there is a different kind of a symmetry theorem that you can define and state and prove for vector surface integrals. And it's not oddness. It's a different thing. It's hard to define. It's confusing to work with. It's more trouble than it's worth. I want to recognize, though, there is such a theorem, but it's not useful in vast majority of cases. In the instances in the long ago past when I have actually spent class time talking about that, it was a poor investment of time, and I've never seen it used what I'll call effectively in problem solving. Okay, so I think this is the last thing before we get to the next section. We've got 10 minutes. That's great. So I want to talk about unexpected analogies between line and surface integrals, specifically vector line integrals and vector surface integrals. Now, let's talk about why they shouldn't have anything to do with each other. Vector line integrals are motivated by the physical concept of work. Vector surface integrals are motivated by the physical concept of flux, which is a completely different physical concept that happens on a completely different geometric object, namely a surface instead of a curve. based on the physical applications that motivate them, you would not expect for vector line integrals and vector surface integrals to have anything to do with each other in any way. Right? And at this point, that's kind of where your mind should be. It should be on, well, these are totally unrelated concepts. Right? So again, I like to point out when there's cool coincidences that happen. Interestingly, both line integrals and surface integrals, vector line integrals, vector surface integrals, they're examples of differential forms, which again we can't talk about. But we don't need to talk about differential forms for it to be a bit of an eyebrow raiser to realize that line and surface integrals, they're different examples of the exact same construction. How about that? Right? There is a mathematical way to unify these. They are the same thing in a appropriately generalized sense. Now, just with that information, not even understanding anything about the math of differential forms, the mere fact that they are both examples, they are both special cases of the same thing, highly suggestive that maybe there should be evidence of this shared background, right, in the way the math lays out on the page. So now I have not talked at all, to speak of anyway, I'm just going to say at all about what those analogies are, but I want to talk about that now. And so here's a picture of a parameterization of a curve. Apologies for the fact that I kind of had to, use kind of verticality in order to have enough space on the page. I wanted to have vector line integrals on the left, vector surface integrals on the right, so we can do comparisons. So I had to make that, the parameterization's angled downward. I know it looks weird, I'm sorry. And here's a picture of a parameterization of a surface. There's nothing new on this page. Everything that's written here is stuff we've talked about and drawn pictures of and written down algebra for in the past. Right? So ditto, all of this algebra, none of this is new. Right? But when you look at this algebra and you look at that algebra, they don't look the same at all. None of the objects in there are the same as any of the objects over here. So why are we interested in this? And what I'm going to do now is I'm going to go through and do some color coding, right? And I'm going to highlight on the page, color by color, the various participants and talk about the roles that they play. Okay, so the velocity vector. There's the velocity vector. I claim that it is in strong analogy with the parameterized normal vector for a surface. For one thing, they both are, if you think about it, derivatives of the parameterization, right? Where does the velocity vector come from? Well, it's literally the derivative of the parameterization. Where does the normal, capital N, come from? Well, it's there's a cross product of derivatives of the parameterization. So these are both, in their ways, derivatives of the parameterization. And now let's see, in the algebra, they appear in analogous places. How about that? Okay, now, let's see, next, the unit tangent vector and the unit normal vector. That, of course, is the parameterized unit normal. Let's see here. Okay, here's a capital T, here's the little n. They appear in analogous places there. Let's see here. Let's talk about the dx vector and the ds vector. There's my dx vector. Here's my ds vector. And notice they appear in analogous places in the algebra. It's starting to look suspiciously analogous at this point. Right? And we can keep going. Let's talk about I have to make a color choice here. Let's use blue. How about that? The ds scalar representing the size of that piece of curve. The capital S scalar representing the size of that piece of surface. Well, again, analogous. Everybody see what I'm talking about here? Very strong analogy here. So, and then by the way, likewise, when you look at the algebra below that follows, when we write down vector line integrals, vector surface integrals, and let's see if I'm going to be as quick as I can here, but the velocity vector and the normal vector. Let's see, the t vector and the n vector. The dx vector and the ds vector. I left out the ds scalar and the other ds scalar. So the analogies just continue preposterously. No way this is a coincidence, right? So 2 reasons I like to show you this. One, very quickly, again, I think it's culturally valuable. I think it's important to know, even if you don't know what differential forms are, to know that they have a very heavy hand in all the stuff that we're learning here. Everything that we're seeing with vector line integrals, vector surface integrals, we're basically looking at special cases of differential forms. I think it's just good to know what you're doing, right? Even if you don't know exactly what that means. Culturally, these are strongly related. But now from a pedagogical point of view, I think it's really valuable to know about analogies when they're there. For example, you might be at a point where you're I got to admit, I'm having trouble understanding the capital N vector. It seems kind of mysterious. What's its deal? What's the deal with that capital N vector? Well, this gives a partial answer to this. The capital N vector, it's kind of playing the analogous role to the velocity vector. Right? And so this might help you get some intuition or some satisfaction, comfort with the idea of there being a capital N vector in here, and maybe get a little bit more comfortable with how to think about it, because it's got a clear analog amongst vector line integrals, and the velocity vector is intuitive. It's really intuitive. Right? The second reason, let me make the analogous point, by the way, with what's the deal with the ds vector? Well, it's analogous to the dx vector in every way, right? The dx vector has these relationships, the ds vector has those relationships, strongly analogous. Okay, so good to know, if only for cultural reasons, but also this is a foot in the door to help you understand some of the particulars about one side or the other. To whatever extent you understand the one side, this gives strong suggestions for how you should think about the other side. All right, so let's see here. I tell you what, this is a lovely stopping point, and I'm going to give you all the remaining minute and a half. I'm sure I owe it to you, so we'll call it here, and see y'all later. Have a good one. See you on Friday.